Okay, so if I mod 9 is equal to 0, or I mod, what, 13? Is equal to 0, or I mod 27 is equal to 0, or I mod 81 is equal to 0. If any of those things are true, including all of them, or including some of them, if at least one of those things are true, we're going to increment count to be 1 bigger than it used to be. In the end, we'll print out count. And what should the number be? 179,487. Okay. So that is the number of numbers between 1 and 1 million that are evenly divisible by any of these guys. Some of you, when you were asking questions, you were confused and thought I was talking about being evenly divisible by all of these guys, which means you would change the ors to ands. This is saying numbers that are evenly divisible by 9, 13, 27, as well as 81. Make sense? It means it's evenly divisible by all of those. Should be a much smaller number. Make sense? A lot fewer numbers are evenly divisible by all 4 of those than are evenly divisible by at least one of them. Go ahead.
On my 15 system, I'll print in.
Mm-hmm.
When I was doing the Hello World assignment the second time, when I didn't print in, it would run. So I took the in out and ran. So I did the same thing.
It's not print n, it's print ln.
Oh, that's an N. Oh,
ln.
That's what it is. Okay.
Yep, print ln.
Okay. My contacts are always ready, so okay, there it is. Correct.
All right, that makes sense?
Yep.
All right, so this is a solution to your homework assignment. I suppose you could have done it maybe a different way, but this was, I would think, the most straightforward way to accomplish it. All right. Is that my thing or somebody else's? Oh, it's fine. I just wanted to make sure it wasn't my computer doing it because I'm concerned this is going to kick off again. It's not bothering me. I just want to make sure that this thing's going to keep recording. Let's see. Exam paper. This is week 2. Okay, so this was dealing with Java and the first version of Solaris. So some people asked some questions about that. I wanted to specifically look at performance, security, hardware compatibility, and user experience. I'll just spend just a couple of minutes just talking about this at the high level. I don't want to spend too much time on it. But from performance, we should have been looking at a reduction in performance because of the virtual machine. Some of the things you may have noticed in your research is that only certain aspects of the operating system were written in terms of Java. Other aspects remained in an older language like C or C++. So it wasn't an overall performance hit, but the aspects of the operating system that were written in Java should have taken a performance hit. At the same time, security should have improved because now you had portions of the operating system compartmentalized inside of the Java virtual machine. So they were separated from each other. So if one part died, another part was protected. So Java hurt performance but increased security. Hardware compatibility, it depends how you approached this question as to what your answer was. If you were looking specifically from hardware driver support, probably would not have been a significant change. You know, the older Unix operating systems were already pretty specific about what hardware they supported and what hardware they didn't. If you approached it from the Java virtual machine perspective, running on various hardware without having to worry about the drivers, where the driver is abstracted, you could have maybe said that it was available for more pieces of hardware now because Java, the Java virtual machine aspect of the operating system is what understood hardware. Okay, that's what was implemented as far as the hardware in the machine, and now you had aspects of the operating system written in terms of that Java virtual machine, as opposed to in terms of hardware specifically. So could have approached that a couple of different ways. I guess I'll just look at what you said. User experience, probably a similar type argument, depends how you approached it. When they did the overhaul to move it to an Intel-based operating system using Java, at the same time they added a whole new user interface, so they had dancing things. This was back in the day when Java was kind of the cool kid, and you could have little dancing guys around on the computer making your desktop seem like it was alive. So kind of like today when we sometimes have jumping icons letting us, bringing our attention to it. Back then that was starting to happen, maybe when the performance wasn't really there to support that. So you might say that the user experience maybe was initially cooler, because like, oh, this is kind of interesting, this stuff is happening. But in the end, maybe it was less user-friendly because you felt like the interface was kind of sluggish because of so much Java stuff going on. So you could have argued a couple of different ways with that. Probably the big points was talking about the trade-off between performance and security. Java added security to the operating system, which is important. We want our operating systems to be secure at the cost of some performance, which is also important. We want our operating systems to be fast. So it becomes an interesting trade-off. If it helps, none of the operating systems today are written with Java. And it heavily incorporated into the operating system. So clearly in that case, the security benefits did not outweigh the performance hit. So we went back to operating systems written in terms of faster performing languages, and then we came up with other ways to make it more secure, or just forgot about security and just cross your fingers and hope for the best. All right. So just real quickly, I've been getting that weird error today. Let me just restart Eclipse. So we need to talk about the different types of loops. So right at the end of class last time, I kind of gave you the starting point for a loop and said, this will go through all the numbers between 1 and a million. But now we need to talk about the various types of loops that exist in Java. So again, we have this idea of how do human beings solve problems. We remember things, we ask questions, we use repetition. How do programming languages emulate memory? Through variables. How do they emulate asking questions? Through conditionals, if statements. And how do they emulate repetition? Through loops. Okay, in Java, we have 3 different loops available to us. Actually, we have a 4th, but it's related to a for loop. I'll mention it here in a second. So 3 different generic loops. We have for loops, while loops, and do while loops. Each loop lends itself to a different type of problem. Now, having said that, I will go out and say that every problem that can be solved using loops can be solved using any of the 3 loops. Okay? But each loop kind of is created for solving certain types of problems. So if you applied that loop to that kind of problem, it's going to be an easier fit than trying to force one of the other loops to solve that problem. So we'll talk about those. So a for loop, it's what's called a precheck loop, which lends itself to counting problems. Okay, so let's write all 3 of them out, and then we'll talk about each one in detail. A while loop is a precheck No, I'm going to have to hyphenate it. Loop, which lends itself to problems where we do not know how many times we must repeat. Do-while loops are post-check loops where the body of the loop, well, here, let's see, post-check loops that lend themselves to problems where the body of the loop must execute at least one time. Okay, and we'll talk about each of those. All right, so this is kind of your cheat sheet, if you will. 3 kinds of loops: for loops, while loops, do while loops. For loops are pre-check loops. Go ahead and put our hyphen in there just to be consistent. Pre-check means that we ask the question. We look at the Boolean expression before we execute the body of the loop even one time. So for loops and while loops both execute 0 or more times. There is no guarantee that the stuff inside of the loop will ever happen with a for loop and a while loop, because both of them are pre-check loops, so they ask the question first. Okay, I'll show you examples. As the alternative is do while loops ask the question at the end of the first iteration through the loop. So they are guaranteed to execute the code inside the loop at least once. Okay? And do while loops lend themselves to those kinds of problems where you have to do something at least once. So, for loops, pre-check loops, and they lend themselves to counting type problems. You could even reword this a little bit and say they lend themselves to problems where we know how many times we have to loop, as opposed to while loops, which are pre-check loops that lend themselves to problems where we don't know how many times we have to loop. All right? And just kind of out loud, let's talk about a couple of these. For instance, let's say I want to count between 1 and 1,000,000, like we did in our homework assignment. We knew that we wanted to count through 1,000,000 times, right? We knew exactly how many times we had to loop. For loops lend themselves to that kind of problem, okay? And if you remember, we used a for loop for that problem, okay? Counting problem. We knew how many times we wanted to loop. Now, while loops, just kind of talking at the high level here, since they lend themselves to problems where we don't know how many times we have to loop, they lend themselves to problems like press any key to continue, which is less common now because most of our stuff are graphic user interface applications. So maybe they say click OK to continue, right? Okay. How long will it be until we click OK? Well, it might be a second, might be 5 minutes, might be 5 weeks, right? Have you clicked OK? No. 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 We don't know how many times we're going to have to spin. But we're just going to keep asking that question over and over and over again. Do you finally click OK? Make sense? That's the kind of problem while loops lend themselves to. Okay? And definitely want to ask the question at least the first time. Okay? But if they already clicked, we're not going to wait. But we don't know when they will finally click. Do while loops. Well, first of all, these first two are going to be our most common loops. Probably the loop we see most often will be a for loop. Okay, this is the loop we'll see most often. Because in computer science, in computer programming, a lot of stuff we're doing deals with counting. We want to do something 10 times. We want to look through all the numbers between 1 and 1,000,000. Stuff like that. Okay, very defined counting problems. So we see a lot of for loops because of that. Now, while loops will certainly be the second most common. In a distant third, do while loops. You will not see very many do while loops in programs. Now, having said that, some of our most common problems are actually solved using a do while loop. So, just to recap here, a do while loop is a post-check loop, so we don't ask the question until after we perform the body of the loop at least once. And they lend themselves to problems where we must perform the body of the loop at least once. Good example of this is authentication. You have to put in your username and your password for your email at least one time. You get one shot. If you screw up, it asks again. Okay, but you have to put it in once, right? So please enter your username. Please enter your password. Most of our web browsers will ever have it stored for us, but we trust that it's actually sending the data again, right? We just didn't have to physically type it. So we enter our username, enter our password. It sends it once. If we are authenticated, we're done. If we're not, we probably screwed up. Ask again. Ask again, so on and so forth. But we need to send it at least once. Okay? So while do-while loops are the rarest to see in a program, the problems that lend themselves to being solved with a do-while loop are extremely common. I mean, we could just go through our whole world, and everything requires authentication, right? So we have to do things at least one time very, very, very often. Just happens to be that computer programs do a lot of mathy stuff. Okay, and authentication tends to be just a little piece. Happens one time. Once you log into Amazon, there's a whole bunch of extra complex crap that's going on behind the scenes that deals with math and for loops and all sorts of stuff like that after you authenticated once. So you have 200 for loops following that one do-while loop. Make sense? Okay. So those are our three kinds of loops at the high level. Let's look at the syntax for each of these. We've already seen the syntax of the for loop, but I kind of just gave it to you and said, by the way, this works. Let's talk through the actual syntax and understand how it works. So I'll deal with each of these individually. So let's start with the for loop. Let's do a text box here. So make that left justified. Syntax for a for loop is for opening parenthesis. Followed by a variable definition. Okay? We could actually say var defs if we want to be precise here, and I'll explain that in a second. Okay? Followed by a semicolon. I'll put a little space there to separate. Okay? Followed by a Boolean expression. What's a Boolean expression? Any expression that boils down to a single value of true or false. Okay? Followed by a semicolon. Followed by just say var change. Here, just so we say complete here, I'll say var changes. So I would refer to this as the loop header. So the word for, all lowercase, followed by an opening parenthesis, followed by 0 or more variable definitions, followed by a semicolon, followed by exactly one Boolean expression, followed by a semicolon, followed by 0 or more variable changes, adding 1 to I, subtracting 1 from I, stuff like that. Opening curly brace. I'll put the closing curly brace in there as well right now. Zero or more statements. Okay, so for loops. Have this header, opening curly brace, followed by 0 or more statements, followed by a closing curly brace. Now remind me, when we talked about if statements, did we discuss that you don't actually need the opening and closing curly braces? Did I mention that?
Just one.
But did we actually talk about it? Somebody don't lie to me. No? Okay. We'll talk about with loops then. Okay. It's a very important concept. I argue that you always should use the opening and closing curly braces. It's never wrong. Okay, it's never wrong to use the opening curly brace and the closing curly brace with an if statement. It's never wrong to use the opening curly brace and the closing curly brace with a for, with a while loop, with a do while loop. It's never wrong. If you choose to get fancy and say, oh, I'm going to save myself a couple lines because I don't actually need them because I know what I'm doing, if you really know what you're doing, that's fine. But if you don't really understand the concept, you could run into trouble. And I'll show you that today. We'll look at it here in actually a few minutes with the for loop. Okay, so here's the generic syntax for a for loop. So as I'm advertising it, I'm saying that the opening and closing curly brace is part of the formal syntax. The real formal syntax would look like this. Well, actually it would look just like that. Statement. The most common statement to be there is the block statement, which is the opening and closing curly brace that is a container to hold 0 or more other statements. But I like this approach. Always have opening and closing curly braces and you'll never be sorry. Plus, I think it makes your code look more structured. All right. I think one thing that beginning programmers, even more advanced programmers, tend to do is they want to minimize the number of lines of code that they write, and I don't get it. I've been programming for a while, and I don't write opening and closing curly braces just for class. If I'm writing my own code, I put the opening and closing curly braces in there. I think it just makes your code look more structured. You're less prone to mistakes. Nobody's impressed if you saved yourself 2 lines of code and introduced 7 bugs. You understand? So I guess don't be a hero. So let's look at a legitimate example of a for loop here. So for var defs, we can define 0 or more variables here. I'm going to go ahead and I'm going to define a single value here, and we're going to actually put this into Eclipse, and we'll do some drills with it, and you'll see what breaks and what doesn't break under different circumstances. So int I is equal to 0. Might be what you would do. So what does this look like? This looks like a variable definition, correct? Variable definition, the generic syntax is type, followed by variable name, followed by a assignment operator, followed by a value. That makes sense? Now, when you look at other people's code, like if you were researching on your homework assignments or something like that, you probably noticed in for loops, variables named I, J, and K are very, 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 very common. Okay, this is just a naming convention. Typically, when we're dealing with loops like we did in our homework, that variable I, this guy right here, he was a throwaway variable. He didn't have any meaning. You know, we didn't have a variable called, string name equals Mike. That variable didn't have meaning. We just used I as a placeholder to hold all the numbers between 1 and 1,000,000. Does that make sense? So it's relatively a throwaway variable, and single character variables like this for throwaway variables are very convenient because they're quick to write. I could say I mod 9 is equal to 0. As opposed to the current number mod 9 is equal to 0. Or the current number mod 13 is equal to 0. Or the current number mod... Get where I'm going with this? Okay. You should always name your variable something appropriate if your variable has meaning. In this case, and I'm going to show you this in a few minutes, this variable I lives and dies with this for loop. As soon as that for loop's done, I's gone. It's as if it never existed. Okay? It's literally a throwaway variable. Okay? We only brought it into existence temporarily to support this loop. All right, so it's fairly common for loops to use variables like I, J, and K. And kind of that's the 3 of them. If you have a single loop like this, it's almost always I. If you have a loop inside of a loop, it's almost always I and J. A loop inside of a loop inside of a loop is I, J, and K. And the reality is if we're having loops inside of loops like that, we're probably doing something with either a 2-dimensional grid or a 3-dimensional cube. Why don't we have a 4th one? Humans stop staying sane when we start thinking about things in 4 dimensions. So typically your programs, when somebody's writing a program, every now and then somebody might be working with a 3-dimensional graph or something. And if they're doing that, they might have a loop inside of a loop inside of a loop to deal with the x-axis, the y-axis, and the z-axis. Okay? Usually we're dealing with 1 or 2-dimensional things. Most of the time it's just a single-dimensional thing like this. But if you're dealing with a grid, the x-axis and the y-axis, you might decide to use I and J. I don't know why they don't use X and Y, but they just don't. You are welcome to if you'd like to buck the trend. But, I, J, and K tend to be the common throwaway variables for loops. You can call this guy Elephant if you want. But if you name him Elephant up here, you need to refer to them as elephant in here. Okay? So int I equals 0. We're just going to define a single variable there. If we wanted to define more variables there than that, we can do a comma. Int j is equal to 5 for no good reason. I just decided to make it 5. So you are allowed to define multiple variables there. Very rare, you'll see this. Very rare. So most of the time, your loops will start just like this. For, opening parenthesis, int I is equal to 0. And when I say most of the time it'll start like this, I don't mean like this, I mean exactly like this. It'll be those exact characters. Every now and then it might be something dot length, because you might start at the end of something and work towards the beginning. Okay? But typically it's going to be starting at 0 or starting at some maximum index and walking backwards, subtracting 1 from it each time instead of adding 1. But this is going to be a very common pattern for us right here. Int I equals equal to 0. Boolean expression. Let's put in I less than 10. Variable changes. Again, this is usually the place where we update the value of whatever we defined over here in our variable definitions. So we might say I is equal to I plus 1. If we want to modify another variable, we could say, comma, j is equal to j minus 2. For no good reason. But, okay, so if we wanted to take advantage of that section to update more than one variable, we can. Commonly, you wouldn't see that. This is something we would see very often. A setup like this. Maybe the only thing that would change is the 10. Because remember, for loops lend themselves to counting type problems. This guy loops through 10 times. It starts at 0 and keeps going as long as I is less than 10. So it's 0 through 9 inclusive. And we add 1 to I each time. So this is our loop pattern for doing something 10 times. If I put an equal sign in there, now we're doing something 11 times. If I change this to 1,000, now we're doing something 1,000 times. Make sense? These are the kinds of problems for loops lend themselves to. Now, order of operation as far as how we go through for loops. The variable declaration part happens exactly once, and it happens first. So right when this loop is first created, we process the variable definitions section. And in this case, we create a single variable named I, capable of holding an integer, and we start it off at 0. After that one-time instantiation, we never execute this part of the loop again. Happens once and happens first. Now, remember, for loops are pre-check loops. So we ask the Boolean in question before we execute the body of the loop. So after we've defined our variables, before we go down and do whatever we're going to do in here, so let's just put some sample code. We'll just print out I to the screen. Okay, so before we execute the body, whatever's in between the opening and closing curly braces, which is to print out the current value of I, we ask this question. I less than 1,000. So I started off as 0. So we now have a variable called I that currently has a value of 0. Then we ask the question, is I less than 1,000? Current value of I is 0. Is 0 less than 1,000? Is that a true statement? That's true. Since this is true, we will execute the body of the loop. Then we hit the end of the loop, the last closing curly brace. We spin back up, and we execute the var changes section. In this case, we're saying I, you now equal whatever you used to equal plus 1. So I used to be 0, now I is 1. Then we ask the question again. Is I less than 1,000? Current value of I is 1. Is 1 less than 1,000? Yes. Print out 1. 1 becomes 2. Is 2 less than 1,000? Yes. Print out 2. 2 becomes 3. 3 less than 1,000? We're going to just keep going. This might take a while. Okay. I is now 999. Is that 999 less than 1,000? Yes. We'll print out 999. 999 becomes 1,000. Is 1,000 less than 1,000? It's not less than it. So we fail. This is false. As soon as we get a false there, we drop past the end of the loop and continue on. We do not execute the body that last time. So when I was 1,000, we fail here. 1,000 is not less than 1,000. So we just fall past the end of the loop, and now the loop is over. We just keep going. We've finished our repetition, whatever we were trying to accomplish with that. Make sense? Okay. So, let's go look at a couple of examples here. Everybody okay with me getting rid of this code? As the class goes on, I'll be deleting more and more complex chunks of code than that. And you're like, that's just gold. How long it took me to write that? It just gets in the way. I want practice. Every now and then when I'm teaching some of my classes, I start writing in the wrong language. I program commonly into several different programming languages. So there's been times I was teaching a Python class, jumped into Java, or maybe vice versa, something like that. It's all the same crap. Okay, so what we're going to do is we're going to create a quick little loop for int I is equal to 0, I is less than 10, I is equal to I plus 1. At some point I'll teach you I plus plus and plus plus I, so I don't have to type I equals I plus 1 anymore. But for right now, that's all you know how to do. And then we'll print it out. Okay, so this is our common loop that'll do something 10 times. What are we going to do 10 times? We're going to print out the current value I. So this will print out 0, then 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9. 9 becomes 10. Is 10 less than 10? Nope. So we'll fall past. So this will print out 0 to 9. So go ahead and run it. We'll see that's true. Make sense? So in this case, we've linked what we're printing to our value we're spinning. But I could decide just to print my name 10 times if I want to, right? This is just repetition. That's the problem it's solving. Do something 10 times is what this loop says. What am I doing? I'm going to print Mike out 10 times. There we go, 10 Mikes. Make sense? Okay, you're under no obligation to link what you do in here to what you're doing up here. The purpose of a loop is to emulate the human problem-solving approach of repetition. Do something so many times. All right. Okay, now I'm about to trick you. Are we ready? All right. So, remind me again, this printed out, I switched it back to print out I now. So this went from 0 to 9, correct? Then 9 became 10. Is 10 less than 10? Nope, so I was equal to 10, correct? So what I'm going to do then is I'm going to come past this. And we should be able to see that 10. So I'm going to print out I after the loop. What's going to print out?
Can it read the I out of the loop?
Okay. We're confused a little bit, right? Let's not pay too much attention to the red marking there. Okay. It's going to give us an error. Okay. So if I hover over this, it's going to say it's never heard of a variable called I. I cannot be resolved to a variable. Now remember earlier I said that variables that we define in here are typically considered to be throwaway variables. They live and die with the loop. Okay? So this variable right here disappeared as soon as our loop ended. Now, if I instead said int I here, let's start it off at, here, I'll trick you again. Start off at 500. Now in here, I'm not going to define I. I'm just going to set I to a starting point. So I defined I outside of the for loop, before the for loop. Then, in my variable definition section of the for loop, I just set I, which is a variable, equal to a new value, 0. Go through, print out 0 through 9. 9 becomes 10. Is 10 less than 10? It's not. So we fall past the loop. What's going to print out here? But I start off as 500. It's not going to go back to its original value? We got a couple people who think it's going to be 500.
And maybe because it's already changed, you set it to 0, so.
Okay. As soon as we set I equal to 0 here, it was as if this 500 never happened. We overwrote that value. Gone. Okay? We dumped out what used to be an I and put a new value in there. Make sense? So this will print out 0 through 10. 0 through 9 gets printed out inside the for loop. Then when we exit the for loop, we'll print out the current value of I, which will be that final value of I when I went from 9 to 10 and we failed the Boolean expression. Make sense? So we'll see 0 to 10. Make sense? All right, so notice that if we define the variable outside of the for loop, we can access it outside the for loop. If we define it in the for loop, we can only access it within the for loop. Make sense? This concept is known as variable scope. Okay? Variable scope means where can you access a variable? Kind of a fancy word that means where can I access this guy? Okay? Variables always resolve to their most local definition. Variables always resolve to their most local definition. And to explain what that comment means, let's go back to what we just had a second ago. Okay, so now we're back to our broken code, right? So, for loop, the I is defined inside the for loop. The loop runs perfectly fine, no harm, no foul. 9 becomes 10. We fail here. We drop out of the loop and we try to print out the current value of I. Well, in order to print out I needs to be resolved to its value. Okay? And as I pointed out over here, all variables resolve to their most local definition. All variables resolve to their most local definition. So, we're going to try to resolve the variable I. What is the most local definition of I? There isn't one. This definition of I has died. It's gone. It's as if it was never defined. Make sense? Is there any definition of I inside of this opening curly brace and this closing curly brace that wasn't in here? Nope. Is there a definition of I up here inside this opening curly brace and this closing curly brace? Nope. So, this is a variable environment. A for loop creates its own local variable environment. The next level up is the variable environment created by this method, and we'll talk about methods today. The next level up is the variable environment created by this class. Okay? There's actually another level up for if we're a child through inheritance if we are dealing with parent classes, but for right now we'll just deal with this. Okay? So, a variable always resolves to its most local definition, and we look for variables in our local environment before we go up to the next global environment. Okay? And to kind of paint this picture here, I'm going to steal this code. Because variable environments are pretty important. So there's our code. And what I'm going to do is I'm going to color code some environments here. So I'm going to create a shape. There's one environment in the blue. Create another shape here. Change the color of this guy. There's another environment. There's another environment. Now, when I was here looking at I, trying to resolve the value of I, notice that my local environment is this red environment, not this blue one. Okay? So in terms of this line of code right here, the local environment that we're going to try to resolve that variable in is the red environment here. The blue environment is already gone. We don't have access to that environment. We're outside of that environment. Make sense? So from the position of this red environment, we have access to the red environment and the green environment. From the blue environment, we have access to the blue environment, the red environment, and the green environment. Okay? And to show you that, what I'll do here is I'll say int num is equal to 7. Let's go ahead and get rid of the I there. And I will print out num inside here. So again, this loop does something 10 times, right? What does it do 10 times? It prints out the value of num. Well, num is a variable. It'll resolve to its most local definition. Where are we going to look first? We're going to look in the blue environment. Do we see a definition of num in the blue environment? Nope, no definition of num in the blue environment. What's my next local environment? Red environment, right? So that's the next place we'll look. Here's the red environment. Do I have a definition of num there? I do. So num will resolve to its most local definition, which was not found in the blue environment, but it was found in the red environment. So this is going to print out 10 sevens. That make sense? Okay. Now, you don't know what static means yet, just leave it. So just pretend like that's correct. So I defined a variable up here in the green environment now. And this is going to print out 13 10 times. So there's 10 13s. So when I want to print this out each time through the loop, it had to resolve the value of blah. Every variable always resolves to its most local definition. Well, first it checks the blue environment. No definition of blah there. Then it checks the red environment. No definition of blah there. Then it checks the green environment. And we do have a definition of blah there. Make sense?
So if you define blah in the red and in the green, in both.
Okay.
So the green and then.
You want to say that?
Yeah.
All right, like that? A variable always resolves to its most local definition. Always resolves to its most local definition. Well, do we have a blah defined in the blue environment? Nope. Do we have a blah defined in the red environment?
Yes.
We do. We won't look anymore. This will print out 10 sevens. Even though we had a blah defined up here, this guy is said to shadow it. Okay? We have a more local version of the variable called blah. That makes sense? Go ahead.
These will be up on the Angel site, right?
I think they already are. You mean the videos?
Yeah.
The videos are already up there.
Oh, okay.
Yeah, so I upload them and there's a link up there. The slides are also up there. I have a link to all the slides too. It's just shared, so they update in real time. All right, so that scoping rules make sense? All right, so this statement right here, variables always resolve to their most local definition, is a super important statement. As long as you understand how environments work, how variable environments work. Okay? When we're dealing with for loops have a special ability, that is, they are able to create their own local environment that lives and dies with them. Okay? The other loops can't do this. Do while loops, and while loops do not support this. Only for loops. Okay? Typically, for loops are counting loops, and it's going to be pretty common for us to have throwaway variables that we're using specifically for counting for a very short period of time. That's why for loops have these built in. Okay? Now, I would say typically a reasonable rule of thumb is to say that anywhere we have an opening and closing curly brace, we likely have a variable environment. It's probably fair to say that. There's too many exceptions. It's probably fair to say that any place that you have an opening and closing parameter, or open and closing curly braces, it is a variable environment unless it's associated with a while loop, a do while loop, an if statement, or a switch statement. Outside of that, we don't know about switches in here, so just pretend like you didn't even hear that. Okay? Outside of that, it's likely a variable environment. It might be easier to think about it the other way. Today we're going to learn about methods after we talk about loops. This is the main method. We'll be talking about what the main method is, but we already have one method at our disposal. All methods have a variable environment associated with them. All classes have a variable environment associated with them. And so do for loops. It's easier to think about it that way. Everything that's a class or a method has a variable environment associated with it. And as a special case, for loops do as well. It's easier to think about it that way than to think about all the exceptions. Okay? So this blue environment we've created here really is a special case. It's only associated with for loops. And I'll update this when we look at a while loop here in a second. So right now we're back to our loop that prints out all the numbers between 0 and 9. Okay? Now I'm going to write the while loop version of this. I'm going to write it underneath this one though, so we see both. So I'm going to say int I is equal to 0, while I is less than 10, system.out.println I is equal to I plus 1. So if I run this code real quick, we'll see 0 through 9 followed by 0 through 9. 0 through 9 followed by 0 through 9. So functionally, this chunk of code and this chunk of code, as written, display the same stuff to the screen. Functionally. Okay? Now, what if I do that? Variables always resolve to their most local definition. I was defined here, right? Do I have access to I right here? Yeah, I absolutely do. In our example from the previous slide, this is the red environment, right? So I here was defined in the red environment, and this guy is happening in the red environment. Where's this guy happening? Trick question. Still a trick question.
It's in the blue environment. It prints the details.
Only for loops get their own environment. This is still red environment. This is still the red environment. This guy is happening in the red environment. Only for loops got their own. All right. So if I can steal this code, do I have the artistic gusto to? Hey. So that. Oop. Oh man, look at this. They're going to be writing documentaries about me here. This artistic skill. Ridiculous. All right. All right. I think that's. So we see that the only blue environment we have here is the one associated with our for loop. So the only local variable here is I. And that lived and died with this blue environment. This blue environment inside here has access to the red environment up to where this blue started. So that means that this blue environment here does not have access to this integer I down here. It would if I had it defined before here. Okay? So only stuff, it's still linear in nature. So only stuff that was defined before this blue environment inside of the red environment would be accessible within the blue environment. Okay? Now, notice the whole while loop is happening inside the red environment. So this integer I is defined in the red environment. When I ask this Boolean expression, ask this question here, I less than 10, I will resolve to its most local definition, which is the definition of I defined in the same environment as this Boolean expression is happening in the red environment. When I print out I will resolve to its most local definition, that is the definition defined by this variable in the red environment. When I increment I, same thing. Down here, when I print out I again, I will resolve to its most local definition, which is the definition of I right here in the red environment. Make sense?
It's inside the y or the I equals 0.
Well, this is the definition. That's how you define a variable, right there.
So at 0.
Right here, it started off as 0. So right here, I created a brand new variable named I, capable of holding an int, and I put a 0 in there. Then I asked the question, is I less than 10? Is the current value of I less than 10? Is 0 less than 10? Yes, it is. So I print out the current value of I, print it out as 0. Then I set I equal to whatever it currently is plus 1. So I just became a 1. Spin back up. Is 1 less than 10? Yes. Print out a 1. 1 becomes 2. 2 less than 10? Yes. 9 less than 10? Yes. Print out a 9. 9 becomes 10. 10 less than 10? It's not. So we fail. It's false. We fall past the end of the while loop, and we hit this statement right here, which says print out the current value of I. And the current value of I is 10. Make sense?
So if you, in the while loop,
So there's our 0 through 9, followed by our 0 through 10. Go ahead.
I said, for example, in the while loop, if you define another variable called j, for example, instead of y.
Inside the loop?
Yeah, in the while loop. Instead of y, let's say j.
Okay.
And that value is defined after the for loop. If you call the j in the for loop now, what will happen?
If I call j up here,
Yeah.
so you want me to print out j?
Yeah. And it's defined after the for.
Yeah. Can't be resolved. Doesn't know about it. Yeah, it's linear in nature. Had I defined j before this for loop, it would have had access to it. J is defined in the red environment, which is the same environment that the for loop lives within. For loop creates his own blue environment, but it lives in the red environment. So even though the J was defined in the red environment, it was defined after this guy came and went. That make sense?
Excuse me.
Yep.
That means the J declaring the red environment, we have to affect the ones in the blue, right?
Well, this is an error right now. So, I mean, I can't use J here. Are you saying, what if I say int J is equal to 5 here?
Yeah.
If I say J is equal to 5 here, now this J works. This will print out 5 10 times.
Okay.
All right? And each time through the loop is going to redefine J, a brand new variable named J to equal to 5. So it's kind of waste of memory, but whatever. Okay? But when this blue environment, so at this point, this J is a local variable of the blue environment. And when that blue environment dies, so does this version of J. This is a new J that's associated with the red environment. Okay? But it's not associated with the red environment until after this guy already lived and died. So this guy here didn't have access to this J because this J was created, think about it like history. Okay? This happened in 1902. This happened in 1935. Back in 1902, even though it was in the same world, we didn't have access to the stuff from 1935. Make sense? So.
Excuse me.
Yep.
Can we define an I again in the while loop?
Can I define I again in the while loop? It'll yell at us. So you want to say this. You want to say int I is equal to 5. And why? Why is it yelling at us? It's going to say we already have a variable named I. Because this is the red environment, right? This is the red environment. We already have a variable named I defined in the red environment. So redefining a variable named I is not allowed. I can change the value of I. That's not creating a brand new variable. That's taking an existing variable and putting a new value in it. That makes
What if you define I before the for?
If I define I here before the for loop,
Yeah.
it doesn't like this because of the way that the for loop's special local environment works. It's going to say there's already a variable named I defined. Okay? But the reality is, if I defined I here, I need to make it static, just trust me. It's not going to complain about it here, even though there is already a variable named I. That this guy does have access to a variable named I because it was defined in the green environment. Okay? And that's because of the way that the special environment specifically for for loops works. So this local environment that's defined for loops is defined a little bit different than typical variable environments. It's defined as kind of a sub-environment of the environment it lives in. So if we look at it in terms of this picture here, this blue environment right here isn't a full-fledged variable environment. It's kind of a bolt-on sub-environment of the red environment. So it relies on the red environment for its existence. Okay? Where the red environment doesn't rely on the green environment for its existence. Green environment has to exist in order for it to be syntactically correct, but not for it to exist. This would be called a heavyweight environment. It's a full-fledged, full-feature variable environment. And what we would end up doing is we would stop calling it just a variable environment. We would really call it an environment. Because environments can hold variables, they can hold methods, they can hold more than just variables. This blue environment here is just a variable environment. You could only hold variable value pairs, name value pairs in that blue environment. Make sense? Okay. And as we introduce methods and stuff like that, that'll probably make more sense. But probably the best punchline to take out of this discussion is that this blue environment is special. The red and the green environment are normal environments. These guys act the same. The blue environment kind of has its own little caveats because it's added in there as a feature because of how we use for loops. Okay? And really the only caveat that affects us is the fact that we can't have a variable named I defined in the red environment before the loop and then redefine an I in the special environment created for us as part of the for loop. Those two conflict with each other. But I can say int I is equal to 0 and then just say I there. Or, since I'm wasting my time, why set it equal to 0 and then keep it at 0? I could just leave this part blank. I can choose to do nothing in the variable definition portion of the for loop. Still need to have the semicolon. That guy still has to be there. It's part of the syntax. Okay, the word for, the opening parenthesis, the semicolons, those are strict. That's strictly what the interpreter, well, in this case it's a compile language, the compiler is looking for when it's parsing out the programming language. Those are required, but you don't actually have to have anything there if you don't want. So this is legal code. Now I is defined in the red environment, used in the blue environment. Continue to be used in the red environment. Same I. I is defined right here, which shadows this version of it. So now we have an I in the green environment, which gets put on hold when the red environment starts, because the red environment creates its own more local version of I. Okay, so this belongs to the red environment. This for loop, even though he creates his own blue environment, that blue environment lives within the red environment. Okay, so I variables always resolve to their most local definition. Most local definition of I here is not defined in the blue environment. Instead, it's defined right there in the red environment. So we had to look up. We looked locally in the blue environment, didn't find a definition for I. Jumped up one level to the red environment, found our definition for I. Okay? So this variable resolves to its most local definition, which is the one in the red environment. Okay? Which means after this blue environment dies, this I still lives. And any changes the blue environment made to it are still there. Okay? So I start off at 0. It became 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this blue environment is dead, But I still exists, and now it holds 10, not 0, because the blue environment made changes to it while it was running.
Okay, what about the first I? When will it be?
Well, in this case, this is a waste of time. As our code is written right now, we cannot use this I. If we wanted to, if you want to see this, I can do this. So let's make this guy 500. This will print out that I. So it'll print out 500. Then we defined a more local I. That I is being used here, as well as here, as well as here. So this will print out 500. I start, then I is 0. This will print out 0 through 9. What will that print out? Nothing. Print out nothing. While loops are pre-check loops. So that means we ask the question first. Is the current value of I less than 10? What's the current value of I? It's 10. It's the current value when this for loop finished. Okay? So I, the very same I that made this Boolean expression fail, is the same I that will make the same Boolean expression fail down there. So this doesn't do anything right now. What will this print out? 10, the current value of I. That is this I. The I from the most local definition. So this will print out 500, then 0 through 9, then a 10. Oh, I'm lying because I'm printing out J in here. Now it'll print out 0 through 9. 500, 0 through 9, then our 10. Make sense? All right. So this seems like it's easy to understand when we color code it and stuff. Super powerful concept. Super powerful concept. And if you can accurately identify the scope of a variable, it's one of the most powerful tools you'll have as a programmer. Because by knowing how to do that and remembering this, you will always be able to read your code. You can look at any variable and say, what will this be during runtime? What will this resolve to? And you'll be able to answer it, as opposed to having to run the program and seeing what pops out of the box. You're crossing your fingers and hoping everything works out. Okay? So that's actually a decent time for me to say this. As you're working on your assignments, as they start getting more and more complex, if you find yourself typing in code, then hitting play and seeing if it works, you're probably doing yourself a disservice. You should never hit play. You should never run the program unless you have gone through and read through the code and you feel that there's a chance it will work. You think based on your understanding of programming at that point in time, you think what you've written is legitimate code that should functionally do what you wanted it to do. You don't want to put yourself into a situation where you're just randomly making changes without any thought and hitting the play button to see if it worked. Okay? Because what will end up happening is eventually you'll try everything that can be tried and it eventually will work. And you'll be happy with yourself that you have a functioning program, but you won't be able to repeat it. You won't know what you did. You won't understand the logic you had to go through to make it work that way. Now, there's going to be plenty of times that you hit the play button thinking you know what you're doing. And then you're going to prove to yourself you didn't. That's okay. That's constructive. Make sense? So as long as you're pushing it with intent, I think I understand what I wrote here. I'm pretty sure if I walk through it, it does this, then this, then this, and that should give me what I expect. Then when you run it, if it gives you something different, you're like, okay, why did it give me that? That's a learning opportunity for you to go back through the code and actually see why it produced a result that was different than what you thought. Make sense? Okay? Super important that you go through that experience as you're writing this stuff. Programming is not easy. Okay? Even as you guys were writing this last assignment, which is, I gave you, 90% of the code, you still ran into errors. You forgot a semicolon here. You use ands instead of ors. There were things that you're not practiced at doing that caused you to make mistakes. But the most important thing is you didn't guess. Some of you did, but I want you to move away from that. Because you're in this class to learn. You'll get your grade, whatever the grade is, but who cares what a grade looks like if you don't have that knowledge, right? So programming is difficult because I tell people it's kind of like a sport. It's not something you can just go and study and go pass the test like some of the other classes that you might have. That doesn't devalue those classes. Programming is just a different animal. You don't just walk out in the court, somebody explains the rules of basketball to you, or I guess what, for cricket for some of you? Who's a cricket fan in here? We literally have no cricket fans in here? It's like my go-to move in grad classes. Really? You guys have been in the States too long is a problem. Probably an NFL fan now, aren't you? You like football? Real football or soccer?
American football.
All right, so this is a soccer group, not cricket group. All right, so you didn't just run out into the field for soccer, but the pitch. Soccer pitch, is that it? It's called? I think it's called the pitch.
Yeah.
Yeah, okay. You didn't just run out into the soccer pitch and somebody explained the rules of soccer to you and all of a sudden now you're good at soccer. That's not how it works, right? Soccer's complex. You got to play to know it, and you got to play a lot to get reasonable at it. And then you got to be in good shape, right? There's all sorts of things that play into that. So in order to become proficient in soccer, there were hours. So are you a good soccer player? Or a reasonable soccer player? Somebody in here probably is. Okay, good soccer player, right? Only played a couple times? 2 or 3 times in your whole life you've played? A lot, right? Okay. Hundreds and hundreds and hundreds of hours you spent playing soccer. Right. Well, yeah, and compared to some of the pros, you suck, right? But the point is that to get where you are today in soccer took a lot of practice. Okay, and programming is very similar. You had to make all sorts of mistakes. Now, you don't want to connect it directly to a physical thing like that. Because, soccer, it's about controlling your body and all this. There's a lot more to it than that, but I think it's a decent analogy to say that you have to practice programming. Make a lot of mistakes. Figure out what works, figure out what doesn't work. Figure out how you process stuff in order to get good at it. It's not just something you can memorize and show up to a test and do well. Okay? Okay, so that's scoping rules. So let's finish talking about the while loop then while we're in here. So remember, while loops, let's get this back to the original state. So here's a for loop that goes through 10 times and prints out I each time. So this is going to print out 0 through 9. Here's a while loop that's going to go through 10 times, print out I each time, and this will print out 0 through 9. So we have 2 0 through 9s, 0 to 9, 0 to 9. Now up here, we saw that we could not print out I there because I lived and died with that blue environment. But down here, I can print out I because this I resolves to its most local definition, which is right here, and all that's happening in the red environment. Make sense? Okay. So even though those 2 loops had the same output initially, do we see how the while loop gives us access to the variable after the fact? Yeah. So that's neither good or bad. It's more just interesting knowledge, and we know why now because of the scoping rules, right? When we first talked about loops today, we said for loops lend themselves to counting problems. Hence the reason that there's a local environment. Hence the reason we typically use throwaway variables, stuff like that. That's a counting problem. Well, here's a counting problem right here that we used a while loop for. It worked. Remember when I said you can solve any problem that involves loops with any of the loops? You just might have to do some creative stuff to make it work. All right, so we've applied the while loop problem, the while loop, to a counting problem, when maybe in a more appropriate thing to do create a variable called keyPressed, start off as false, while keyPressed is equal to false. We'll say waiting for a key to be pressed. Okay. What's that code going to do?
It's gonna print waiting for key.
How many times? Well, walk through the code. Boolean key press equals false, while key press is equivalent to false. Is false equal to false?
Yeah.
It is. We're going to print out waiting for a key to be pressed. Spin back up. Is false equal to false? Yep. Waiting for a key to be pressed. Is false equal to false? Yep. Waiting for a key to be pressed. It's an infinite loop. So we're going to get a whole bunch of waiting for a key to be pressed. Okay? While loops lend themselves to this type of problem. Now, because of what we know how to do right now in our programs, we don't know how to get this guy to change. Okay? We don't know how to get this guy to change from an external entity. So we're not capturing key presses. Does that make sense? What I can do here, though, I can simulate it. We'll say int I is equal to 0. Inside here, we'll say if I is equal to 10, key pressed is equal to true. And then each time through here, we'll say I is equal to I plus 1. All right, so we created two variables here. Key pressed is false, and then also a nice little counter. As long as key pressed is false, print out waiting for a key to be pressed. But before we do that, we'll ask a question. If this is the 10th time through, if I is equal to 10, actually I guess in this case it'd be 11th time through, go ahead and flip key pressed to true. So that the next time through the loop, this will fail. That makes sense? So we've kind of simulated a person taking their time pressing a key 11 times through the loop. Now it's done. And we can show that if you... A key has been pressed. So as soon as this loop ends, we'll print out a key has been pressed, and we'll see that it does spit that out. Make sense? While loops lend themselves to that kind of problem. Problems that we aren't necessarily going to be able to simulate too quickly. Lastly, let's look at a do-while loop. Well, actually, before I do that, let's actually give ourselves the syntax for a for loop. Or a while loop, rather, sorry. While, all lowercase, open parenthesis, Boolean expression, closing parenthesis, opening curly brace, closing curly brace. That's the official syntax for a while loop. Now, for counting problems, we typically would, if we were to use a while loop for counting problems, we would typically have var defs before the while loop, var changes at the end of the while loop. So all the same pieces that were in our for loop, in the header of our for loop, exist in our while loop if we're using it for counting problems. And they even get hit in the same order. This guy happens once, exactly once, and it happens first. Then we ask the Boolean expression, because while loops are pre-check loops. Then we do whatever we're going to do. Then we're going to change the variables. So same order. But the official syntax for a while loop doesn't dictate that you ever change variables. Doesn't dictate that you're going to want to define variables. This is the syntax for a while loop. And whatever's in the body of the loop, that guy, will keep happening as long as that Boolean expression boils down to true. Make sense? All right, last kind of loop is a do while loop. That's do, opening curly brace, closing curly brace, while Boolean expression, ending in a semicolon. That's the body of the loop there. So interesting little caveat here, because this is a common mistake that programmers make. Notice at the end of the do while loop only, there's a closing semicolon. Most statements in Java end in a semicolon. System.out.println is a statement, it ends in a semicolon. Int I equals 5, it's a statement, ends in a semicolon. Do while loop is a statement, ends in a semicolon. But for loops and while loops do not end in semicolons. And it's not because they're special. It comes down to the reason why that semicolon is used to terminate the end of a statement. When we send our code through the compiler, it has to be able to figure out whether you've used proper syntax. With the while loop and the for loop, it knows when you've reached the end of the loop because it's a collection of statements. It knows it's either hit that closing curly brace or your final statement if you chose not to use the curly braces. But let's just pretend like you always use curly braces as I've recommended. For a while loop and a for loop, it always knows that you're done when you hit that closing curly brace. For loop, you're done when you hit that closing curly brace. But with the do while loop, the closing curly brace isn't the end. Since it's a pre-check loop, we actually have our Boolean expression portion at the very end. So in order to let Java know that we actually are done with this statement, the semicolon is necessary here. Okay? The semicolon is not optional with a while loop and for loop. It is not correct to use a semicolon with a while loop or a for loop. Okay? And a common mistake programmers make, specifically with for loops, is they get semicolon diarrhea, which I think is phrasing since it also has the word colon in there. Okay? But in any case, when you're writing a for loop, you're already putting lots of semicolons in here, right? And as you become a more advanced Java programmer, you're going to be putting semicolons all over the place because it's at the end of most of our statements. A common mistake beginning programmers make is they throw a semicolon right there at the end of their for loop header. And what that does is it discounts everything that's in there. So all of a sudden your logic doesn't work right and you're looking at it, you don't understand why. It's because your loop actually ended right there. That makes sense? Common mistake. So if you were ever doing something with a loop, specifically for loops, because you already have just written 2 semicolons in a row, so you get a little bit clicky, right? and your code is working, like I've told you a few minutes ago, I want you reading through your code and almost making a prediction of what you think it will do. You notice when before I run code, I make you tell me what you think it'll do? You should be doing the same thing yourself. Okay? I know what the code's going to do. I've read it before. Okay? Plus, I write perfect code. So in any case, you should always be going through the exercise yourself so you know what your code is doing. And if you ever think that the code you're looking at does one thing and you think you understand it and the output's different and you don't understand why, look for stupid things like that. Common mistake, and we all make it. Okay? I rarely make this mistake anymore. There's a good reason for that. I've made it before. I was in a parallel programming class as an undergrad, and we were writing a sorting algorithm that sorted zeros and ones. And for the life of me, I was a pretty good programmer. And for the life of me, I did not know why this thing didn't work. Okay? I traced this thing. I mean, it was like 200 lines of code. I spent hours walking this thing line by line. I was writing the things down on a piece of, like, this works. This took it to the teacher, just like, look at this. What's wrong with it? Semicolon at the end of the line. Took him about 2 hours to find it too. And part of it was because he knew me to be like the best programmer in the class. So he wouldn't assume I would make a careless mistake like that. We don't look at them. That's why you should always have somebody else proofread even your papers, right? When you write a paper and you go and read it, you'll read right past all your mistakes. You made them in the first place. Yeah, always have somebody proofread your stuff because they'll tell you all the stupid mistakes you made that you proofread it 3 times and you read right over them. All right, so that would be a good example of how experience teaches you how not to make some of those mistakes. I rarely make that mistake anymore because I learned my lesson that time. All right. So questions about for loops, while loops, or let me show you a quick example of a do while loop. By the way, I'm tricking you. What's the output of this program going to be? I never defined I. So it's going to say all variables resolved through the most local definition. Well, it's going to look here in the red environment. It's going to say, is there any I's here? Nope. It's going to look in our green environment. Any I's there? Nope. So it's going to come back and say, can't find this guy. Suck less next time, right? So we'll go ahead and make our I int I is equal to 0. Now we have access to it. So the output of this is going to be, we're going to print out. So I starts off at 0. Then we do something. Remember, do while loops are post check loops. So we will execute the stuff in the body of the loop at least once. Guaranteed. Because we do not ask this question until the end. Okay? So I is 0. Print out 0. Print out the current value of I becomes 1. Is 1 less than 10? Yep. Loop back up. Print out 1. 1 becomes 2. 2 less than 10? Yep. So on and so forth. So what will this print out? 0 to 9. 0 to 9. Right? Last time through, printed out 9. 9 becomes 10. Is 10 less than 10? It's not less than it. False, so we fall past it. Can I do that? Is that legal? Yep. I was defined in our red environment. This is in our red environment. Actually, this whole thing's in our red environment because it's not a for loop, so it doesn't get the special blue environment. And for the couple of you that came in late, when I'm saying red and blue, I'm referring to this slide. I colored them red and blue. It's not like a weird Java thing. I could have made this any color. I just happened to make it blue, and I made this red, I made this green. All right. Just wanted to let you know, because if you're ever trying to tell somebody else who wasn't in this class, say, well, that was in the red environment. They're going to look at you like there's something not right. All right. All right. So this will print out 0 through 10 now, right? Okay. What will this print out?
0 with 9 and then 50. No, 0, 50 and then
50 and 51.
yes, 50 and 51.
Is that your final answer? This is the Who Wants to Be a Millionaire? Okay. Got to walk through it. So I won't hit play until we do. Define a variable name I. Start off as 50. Do loops are post-check loops. That means we will print out a 50. We will print out the current value of I, which is 50. Then 50 becomes 51. Is 51 less than 10? Nope. Fall past that. Print out the current value of I, which is 51. This will print out a 50, and then it'll print out a 51. Make sense? Okay, understand why that's what it printed out? That's something you want to get good at. Is being able to look at code and read through it. Slow yourself down. Because initially, programs will always look tricky. You'll look at that and say, oh, well, this is what it's going to do. Okay? Because at a glance, you think it's going to do one thing. You got to look at it in the baby steps. This goes back to our very first day of class, when I said we're such good problem solvers that we forget how we solve problems. Okay? And as human beings, we're so used to just glancing at something and making a determination. Right? When you're playing soccer, my friend over here is playing soccer, you're not sitting there thinking about all the angles and all these things. You are, but you weren't consciously thinking of it, right? I mean, the amazingness of running down the field at full speed, whipping your leg around, kicking the ball, with all that, the good players who use all this curve and stuff like that, and they hit it with different sides of their foot. There's a lot of mechanics. I just break my leg trying to run. I'd be tripping over my own feet. Then you get a ball involved. Now we're really in trouble, right? So, the point is that there's so many things that you're solving while you're playing soccer that you're not even aware of because of how much time you've put into that. It becomes second nature to you. Okay? You probably have a harder time texting than you do playing soccer because you have less practice. Right? Okay? So the idea here is that when you are looking at code like this, I mean, even me, I've looked at a lot of lines of code. I could probably glance at something like this and pretty quickly tell you what it does. But what I'm really doing is I'm walking through it one line at a time. I'm just doing it very quickly. Okay? So you need to get into the habit of actually resolving the code yourself. Pretending that you are the compiler. You are the Java virtual machine at runtime. What do you expect the output to be? And then see if you're right. Make sense? Very important. Okay, so loops. All right, questions about any of the loops? For loops, while loops, do while loops. Make pretty good sense? Okay, we'll be using a lot of for loops. Let me now show you plus and the minus ops. All right, so we have a plus operator. This increments an integer value. We have the minus operator. That's a dash followed by another dash, but it's weird. We're gonna do this. Nailed it. All right. So this decrements an integer value. Okay, plus plus, minus minus. So for example, if I have int I is equal to 0, and then I say I plus plus, that's the same thing as saying I is equal to I plus 1. Okay? Make sense? All right, now I'm going to trick you. Int I equals 0. We'll do a system.out.println I. What's the output of this program going to be? 0. Easy one, right? Okay. Then I'm going to say I plus plus. What's the output of this program going to be? 0, then a 1. 0, then a 1. Which is the same thing as if I said I is equal to I plus 1. Still a 0 and a 1? Okay. Now, the plus plus operator can come before the number or after the number. So I've shown you it is I plus plus. Again, we have 0 and 1. What if I say plus plus I? Still the same thing. Zeros and 1. Now, when used on a line by itself, the plus plus operator, whether it comes before or comes after, operates identically to saying I equals I plus 1, if the variable you're using is I, when used on a line by itself. Now, we're going to put it inside of our code here. So what we're doing is instead of saying I is equal to I plus 1, this is actually an interesting question to ask. What's the output of this program going to be? Got to resolve it. Interesting little factoid to put in here. So this defines a variable named I, starts it off at 0. It prints out I. So what's the current value of I? 0. So we're good with those two lines, right? All right. This is the one that gets a little trickier. Well, let's resolve it. Forget about the println thing. We know that this guy prints something to the screen, right? That's its job. So we'll come here. We've seen that before. That's how we assign a new value to a variable. This says I gets the value of whatever I currently is plus 1. Well, what is I currently? 0. 0 plus 1 is 1. And we're going to store the result back in I. So this boils down to I, which then boils down to its value, which will be 1. 0, 1, 1. Make sense? So whenever you have an expression like this involving the assignment operator, the assignment operator says assign to the variable on the left. You will always have a variable on the left-hand side of the assignment operator, 100% of the time. If you don't, something went south. All right? So the assignment operator, the single equal sign, not to be confused with the double equal sign, which is the equivalence operator for Boolean logic. This says assign into the variable on the left the value of whatever this boils down to on the right. So on the right hand, I boils down to its most local definition, which will be 0. Plus 1 is 1. We're going to store the value of 1 back into the variable called I. And then I gets resolved down to its value, which is now a 1 that we saw print out. And then just for good measure, we printed out I again afterwards. Okay? So we get 0, 1, 1.
Okay, what plus 1?
What's up?
Plus 1.
Oh, I'm getting there. I'm not going to trick you with that one yet. That's 2 examples down. So I've already advertised that I equals I plus 1 is the same thing as I plus plus. Looks a little cleaner, right? Like that? Okay? What's the output of this program going to be? 0, 1, 1? Okay. Then why is it 0, 0, 1? I said that the plus plus can come after or before. If the plus plus comes after the variable that we're incrementing, what it does is this right there, what I have highlighted, will resolve to I as it is now. And then it increments I after, because the plus plus comes after. Okay? So what I have highlighted there resolves to I, the current value of I, which is still 0. But before this line is done, I will become 1 bigger than it used to be. And that value will be stored back in I. But in terms of me using the value right here, I get a 0. Okay, so this resolves to a 0 and also has the side effect of incrementing I by 1. So this is 0. This will also print out a 0 with the side effect of I now being 1 larger than it used to be, which then allows me to print out I on the very next line, getting a 1. Okay? If I say plus plus I instead of I plus plus, that says do the incrementing first, because the plus plus comes first. So increment it now, then resolve to its current value. So this will give me 0, 1, 1. Make sense? Plus plus comes first, increment first. Plus plus comes second, increment second. Increment after. So this will be 0, 1, 1. Make sense? And the minus minuses work the same way. So if I say minus minus I there, I starts off as 0. It'll print out a 0. Minus minus I will print out a -1. It'll decrement it by 1 right off the bat. Decrement it first because the minus minus comes first. Resolve to that new value, which is -1. And in the very next line, it's still -1. So those will be 0, -1, -1. If I say I minus minus here, now it'll be 0, 0, -1. Because we are getting the value as it is right now. And then we are decrementing afterwards. Make sense? Okay, so this will be 0, 0, -1. Now, another rule of thumb. While this is all fine and dandy, and sometimes, every now and then, it does become handy to be able to increment or decrement in line like this. Just like the curly braces, where nobody's impressed if you reduce the number of lines of your code. If you want to increment I, just say I plus plus on its own line like that. If I say I plus plus here, or I say plus plus I, will it make any difference? No, because I'm not using the value till here. Doesn't matter which side I put the plus plus on right here. Sure, it'll resolve to its current value. Well, in this case, it'll increment first, then resolve to its value, but I'm not doing anything with the value. This line stands on its own. This is equivalent to me saying I equals I plus 1. Right? Just a little bit quicker. Really, this is a nice little format to use for for loops. For int I equals 0, I is less than 10, I plus plus. Instead of saying I equals I plus 1. It's a handy format. Okay, this guy. For int I equals 0, I is less than 10, I plus plus. Then do whatever you're going to do. So that instead of I equals I plus 1. It's easier to type, right? 99% of the time when I use the plus plus operator, it's right there in a for loop. Okay? And that's coming from somebody who I definitely understand how the plus plus and the minus minus work. Okay? I know how it works. Nobody's impressed if you start writing these print statements that are trying to trick people into what the output's going to be. See what I'm saying? Somebody's going to read your code. Now, fine, I can make an argument that fine, if a competent person read your code, they should be able to tell the difference between whether you say ++I or I++. Okay, most of you are IT professionals. You're not going to be programming all the time. This stuff's going to be in the back of your head, and you're going to pull it to the surface every now and then when you need it. Wouldn't you appreciate somebody who writes fairly straightforward code instead of tries to show off? Yeah, you want it to make sense. You know, I understand all you're going to put onto your phones. You're going to have the videos like, oh, what would Dr. Lippman say? You know, 30 years from now, you're still watching the old streaming videos. Nobody's impressed. Every now and then it does come in handy. There's some little problem you're solving where it's like, it would be convenient to take advantage of this little piece of knowledge. I'll give you that. Once in a blue moon. Okay. But typically when you write code, write it with the understanding that somebody else is going to have to read it. Okay. And they may not understand that concept. Same thing with the opening and closing curly braces, which I'll talk about now since I forgot about it. But same thing with this. If they don't understand whether or not you need the opening and closing curly braces, and you do, aren't you better off including them because it makes your code look clean than relying on whether they have this, I wouldn't call it special knowledge, but because of the way programming is taught today, you guys in here are getting substantially more detail than you typically would get in a programming class. So I don't know if that's a good or bad thing, but I've been teaching programming for a long time, and I'm not that old, which makes me kind of weird. But I told you last, I've been programming since I was 9. So I've been doing this stuff for a while. And understanding those details is so important to being able to learn new things as a technologist. I get it that you guys aren't going to be writing software all the time. What's going to end up happening is when you guys go out into your professional IT careers, some of you are going to become tinkerers, where you're going to be building servers and stuff like that. Some of you are going to be kind of that go-to person that knows how to fix any printer problem that's ever existed. Okay? And then some of you are going to be kind of the network admin script writers. And all of a sudden you're going to like, oh my gosh, I'm a programmer. I never thought this would happen, but you won't be writing these applications that, like business applications that somebody on you won't be writing things that look like Microsoft Word. What you'll be writing is these things for cleaning up network log files or creating new user accounts or mass deleting user accounts. All sorts of things that make your life easier. Okay, it's like kind of like Star Wars. You'll become a Jedi. Like, why fight with your hands when you can have a lightsaber? Make sense? What? Or the Force? Yeah, just force push. I always wondered that. Why are they running around with lightsabers so they can cut their own arms off? We can just push everybody off into the... And why didn't Yoda use the electricity fire thing all the time? Didn't make any sense, right? I mean, that's your go-to weapon. All right, so in any case, write your code with the intention that somebody who knows less than you will be reading it. Do them a favor. Make it easy to read. Okay? Let me talk just a few minutes about the necessity of the opening and closing curly braces here. And the same lesson for what I'm going to show you here could be applied to if statements. Okay? So what I'm going to say here, so we'll leave these off for a second. So I'm going to say system.out .println I. Okay, right off the bat, it looks a little weird because we're used to seeing it with curly braces, right? Okay, but notice that Eclipse was nice and it did indent that for us. So it looks a little cleaner, but hey, we'll be unnice. Another thing, Eclipse typically will indent your code for you to make it look more structurally sound. If you're using something other than Eclipse, if you're writing code in Notepad or something, do yourself a favor and indent. Because you don't want that. How many of those do you think I've had to debug and grade? Another cool thing with Eclipse. With Eclipse, whether you're on Mac or PC, you can highlight it all. For Mac, it's Command-I to auto-indent. And for PC, I think it's Control-I. Or you can just right-click, highlight what you want, right-click, and go down to Source, Correct Indentation. And it'll just make it look pretty. Okay? And this comes in handy in situations where, let's say that you had, let's say you had a big if statement, just while I'm on this topic. Just roll with this for now. All right, so we have this if statement, and then we have our favorite 10,000 lines of code in here, which I've represented as 2 lines of code. Okay, trust me, there's 10,000. Then I decide, you know what? This if statement actually isn't needed. So I go and I take this out, and I take this out. Now all of a sudden I have 10,000 lines of code that are indented 1 extra level. Make sense? Well, I can just highlight it all and hit Command-I, and it'll put it back in place for me. Rather than having to backspace on one line, then go to the next one and backspace, 10,000 lines. Make sense? Kind of the niceties that Eclipse does for us.
Excuse me, why is it instead of Control-I? It doesn't work on NetBeans.
Doesn't work in NetBeans. Oh, you're on NetBeans. I said Eclipse on PC. So you're on NetBeans. I don't know what the command is for NetBeans. It's been literally a decade since I used NetBeans. But I'm sure it has it.
Yeah, you said something else instead of Control-I, you just go to the...
Well, I highlight the stuff and I right-click, and it gives you a menu. But you're in NetBeans. This isn't, I mean, it's a whole different application.
Something similar, maybe.
Okay, so I said go to Source. Where's Source? Source, correct indentation.
All right, thanks.
But realistically, I would probably just do a quick Google search and say auto-indent NetBeans. It'll probably just give you the quick little shortcut. All right. I think I showed you this last time, but in case I didn't, a lot of books will indent like this. They'll put the opening curly brace on the top line. I hate that format. I won't take points off. It's a perfectly valid format. This format was created, in my opinion, to make programming textbooks shorter. You only have so many lines. You don't. No, I'm serious. You only have so many lines to print, right? I get it. In this case, the method starts here and ends here. Isn't it a lot clearer where it starts and ends when you have it like that? You can just look right down the left-hand side and you see where those things start and end. So I'd recommend indenting like this, having your curly braces like this. Whatever makes you happy. I definitely wouldn't do the thing where it's all left justified, though. That's bad news. All right, so back to our whether or not we need curly braces for loops or conditionals. So here's my for loop. For int I equals 0, I is less than 10, I plus plus. This is going to print out all the numbers between 0 and 9. Yep, no problem, no harm, no foul. In fact, it prints out the exact same thing as it would have printed out if I would have surrounded this guy with curly braces. Exact same output. Okay? What's this going to output? 0 through 9 followed by Bob once. Once. Okay? Now if you would have noticed, Eclipse actually helped me. It did it like that. I re-indented it just to trick you. Okay? Because of the way this is indented, you might say, oh, both of these things are associated with this loop. The syntax for a loop is this stuff followed by a statement. This is a single statement. This is also a single statement. Opening and closing curly braces is a collection of statements, but it is a statement itself. Okay? So because of the way I've indented this, it looks as if both of these lines are associated with this for loop. The reality is this for loop only controls the first statement following it, which is that guy. So this will be 0 through 9, and then on one line by itself, Bob. Make sense? Which is different than the output if I wrap these guys in curly braces. Now this will be 0 Bob, 1 Bob, 2 Bob, 3 Bob, 4 Bob. Make sense? It's never wrong. Never wrong to use the curly braces. So I would recommend you always use them. Okay? Same thing's true with an if statement. If, well here, let's say int num is equal to 7. If num is less than 10, system.out.println blah system.out.println woot. Okay, and what's the output here going to be? Num is 7. Is 7 less than 10? So it's going to say blah and woot. Yeah, blah woot. Good enough. Let's make num 70. Is 70 less than 10? Nope. What's the output going to be? Just woot. Okay. Even though, based on indentation, we might say, oh, both of these belong to the if statement. They don't. Only the first statement following the if statement belongs to it. So this is going to still print out the woot. Because this guy has nothing to do with that if statement. That's equivalent. Now we can see the separation. Make sense? Once again, it's never wrong to put the open and closing curly braces. We want this guy up there. Anything you want to happen related to that if statement being true, put inside the open and closing curly braces. Run this, see we get nothing. Change this back to 7. Now we get blah woot. All right, questions about any of that stuff? Okay, so let's take about a 15-minute break, and we're going to come back and we're going to start talking about methods as well as strings and string methods. So about 8:22, 8:23, something like that.